Hey everybody, welcome back to another episode of Gnarly Datawaves. This is episode 12, How the Time Flies By, and today we'll be talking about how to migrate from your sort of Hive Hadoop setup to a data lake house with Dremio and Apache Iceberg. So basically the idea is moving that sort of on-prem data lake to a data lake house, whether you move completely to the cloud or partially on cloud on-prem or on-prem. We're going to just talk about sort of that migration story that create that sort of easier, faster, more open platform for your data. But before we go there, I always like to remind you that head over to dremio.com. That you'll see a little button that says test drive. And if you head over there and click that button, you'll have the opportunity to actually try out the Dremio Data Lakehouse with no cost, no obligation. Just kind of, get to try it out, see how it feels. I'm pretty sure you'll like it. So yeah, just head over there to dremio.com and try out that Dremio test drive. Also, just so you know, me and many of the others here at Dremio are co-authoring Apache Iceberg, the Definitive Guide, a new book from being published by O'Reilly. Now, the cool thing is we're going to be offering you this book for free. So if you hit that little QR code there, you can download an early copy of the book. So right now it's the first chapter, where we have many other chapters underway. But if you want to get early access to that, just click that or take a picture of that QR code and you will be good to go and you can get a copy of the book. So go for it. Also coming up on Gnarly Datawaves in the weeks to come, next week we're going to have making the move, 5 factors to consider when migrating from Hadoop to the data lakehouse. So very relevant to what we're going to be discussing in this episode. We'll just continue that conversation in next week's episode. Then in the week after that, we're going to be talking about enabling datamesh with Dremioartic and dataascode. So basically how you can take that datamesh architecture and how dataascode can help you enable that. Okay, and then on episode 15, that is yet to be announced. So keep an eye out in this space for forthcoming episode announcements. And again, you'll see us every Tuesday. Now, with that, let's begin. Today, I will be your tour guide on today's presentation, how to migrate from Hive to the data lakehouse with Dremio and Apache Iceberg. Again, I'm Alex Merced, developer advocate here at Dremio, also host of this show, Gnarly Datawaves, and all around just, tech, enthusiast. Okay, just love me talking some tech. Okay, so first off, let's just kind of talk about sort of why we care about this whole migration story. Like, first, like, what are the benefits of the migration? Because what we're talking about is migrating from sort of a legacy table format that is Hive, okay, which is something you're probably likely using if you're using sort of like an on-prem Hadoop type situation. And there's all these newer formats like Apache Iceberg we want to move to. So we're just going to tell you that story, sort of like what is the problem and what is the solution. So essentially, let's just talk about sort of like why Hive exists. Okay, so once upon a time, you had a world where basically the data lake was just starting. And the technology that really kind of made the data lake a thing was Hadoop. So what Hadoop did, it's basically made it possible to store large amounts of information on cheaper machinery. Because before you'd have to get these like big data warehouses, and the data warehouses needed like these really big, powerful computers. So to kind of scale those on-prem data warehouses, you're buying this really expensive hardware, having to pay really expensive price to third-party vendors to manage that physical infrastructure. It was overall just an expensive ordeal. Okay, so if I didn't need but you're not running top-end analytics on all of that data, so you don't need all that data in that data warehouse. So the idea is but we still want to store that data, so it'd be nice to be able to store it somewhere cheaper. Okay, so Hadoop basically made it possible where you can create a network of cheaper computers that can store loads and loads of data. And then basically people started wondering, hey, like, would be nice to be able to run analytics on that data that's just being stored there. And then you had a framework that's part of the Hadoop project called MapReduce. Okay, and MapReduce, you'd be able to write these, Java code that would then, find the data that you want to analyze in your Hadoop storage and then analyze it. But it wasn't the most fun thing to write. It was very tricky, very difficult. So people didn't really like writing MapReduce jobs. What people like writing is SQL. And this is where sort of Hive comes into the picture. So what Hive did is said, why don't you write SQL? How about what we'll do is we'll create a framework by where you write SQL, and that SQL will be then converted into a MapReduce job, nowadays to like a TES job. But basically what it does, it transpiles that much more easier to write SQL into the less pleasant to write MapReduce. And that's great. Okay, that made using MapReduce a lot easier. But in order to do that, to write SQL, you need to know what is a table, okay? Because bottom line, when you write SQL, you refer to do this on a table, create this table, insert into this table, delete from this table, select from this table. So there has to be a way to recognize a table. So Hive came out with one format in which to be able to recognize what is a table. This becomes known as the Hive table format. Okay, and essentially what it is you have a folder, so a directory on your Hadoop storage, and any files in that folder is known as the table. Okay, basically if you have a folder and there's a bunch of Parquet files in it, all those Parquet files are part of the table. That's the assumption. Okay, so what is this? What is table A? What is table B is dependent on the folder the data files are in. And then when it comes to partitioning, the partitions would just be subfolders. So if we divided up the data by month or partitioned it by month, you would have like a folder in the directory for each month with the data files that belong to that partition. And then the which partitions existed, all these directories would be then tracked by the Hive metastore, which would track sort of like that metadata to make it easier for the engines to know where these files would be located. So essentially that was sort of like the Hive way of tracking what is a table. It was based on directories. So the Hive metastore didn't know which files were part of your table. They knew which folders were part of your table. This made it, very simple to understand, but also led to many of the challenges that would later come up when using this format. Okay. Now, some of the pros of using this format is that it became the de facto standard. It became the standard way you would handle doing SQL and analytics on your data lake, because it was pretty simple to be able to recognize tables via a directory structure. And it works for pretty much any tool you can think of. Okay. Because that structure also allowed for partitioning and allowing for those subfolders to act as partitions, this also allowed for more efficient query patterns. Now, when the engine's going in there and reading the files in the directory, it was file format agnostic. So you could have a folder that's a table, and it could have Parquet files, CSV files, JSON files, and all of that would be just treated as one table. Okay, you could atomically update a whole partition, because again, at the end of the day, what's tracked in the metastore is the directory. So what I could do is I could rewrite a partition to a separate directory and then just swap out the reference to that directory in the metastore. So I could atomically update a whole partition because we're swapping out those directories in the metastore. And at the end of the day, it achieved its main goal, which was creating a consistent answer to what is the table. But you still had a lot of problems. Again, we're not referring to specific files in the metastore. So in that case, there wasn't a good way to atomically update like one file. Like if you wanted to atomically update one file, you'd have to atomically update the partition. So you'd have to rewrite the partition into a separate directory and then swap out that reference to the directory. Not the most efficient thing to do in the world. Okay. Now, if you want to change multiple partitions at the same time, you basically have to do it one at a time. Okay, so then you have the possibility of inconsistency between those changes to those multiple partitions. Okay, because a query can sneak in there between the first atomic transaction and the second atomic transaction. Okay, you couldn't just do them as one big atomic transaction just because of the way Hive was architected. Okay, in practice, multiple jobs going on at the same time on the same data set could also very often not be safe. And because basically once you know what folder the data is in, you still have to go figure out, hey, what are all the files in this folder? So there was all these like listing operations and having to kind of figure out which files to read. It still took a while. So while the partitioning certainly is faster than doing a full table scan, you're still scanning a lot of files you don't need. You're still listing a lot of files you don't need to list. Overall, you still had much slower queries than you really needed to have. Okay, and on top of it, the way partitioning work is you would oftentimes have to create additional columns to act as partitions. So an additional like month column, additional like year column. And if you're the end user querying that table and you're not aware of these extra columns, you oftentimes would just end up with a full table scan instead of getting a more faster partition-based query. And generally, like the table statistics for Hive, like you would have to manually generate them. So it's like every time you did a query, the stats weren't necessarily refreshed. So you'd have to periodically run sort of these like analyze queries to like generate table statistics. So oftentimes when you needed them, they were stale because other transactions are going on, and again, these stats aren't being updated with every transaction. So you had all these kinds of issues. So the answer to that was Apache Iceberg. So like Netflix was like, Well, we want to address these problems. So let's create a new format that addresses these problems. So instead of tracking which folders make up the table, you track which files make up the table. That way you can atomically update an individual file. Okay, one snapshot has a file, one snapshot doesn't. Okay, and then what you do is for even more efficient planning, you break up all that metadata instead of just like one big meta store. What you do is you break it up as a bunch of data across different files that relate to each other. So you create this sort of metadata tree. Okay, so really the meta store, aka the catalog, okay, only really tracks one thing. Where is the physical location of the metadata? And then basically the metadata file actually defines like the schema, the partitioning, the snapshots of the table, like basically all that table level data. And then once you figure out which snapshot you want to scan, that's where you visit the manifest list, which documents the individual snapshot. And then basically the files that make up the data are all grouped into different manifests. Okay, and so each snapshot lists all the different manifests that contain the files for that particular snapshot. And using the metadata at the manifest level, you can then prune data that's in partitions that aren't relevant. And then using the data, the individual file metadata in the manifest, you can prune individual files whose data isn't relevant to your query either using min-max filtering. So basically through this journey, you plan a much more efficient query pattern that only scans the files you need to scan. So you're gonna end up having the narrowest scan basically query plan possible. Okay, so that's the benefit of Apache Iceberg. So it's going to allow us to have much faster query plans, but it's also going to allow us to have more consistency and safety across the board on all types of transactions to be able to have like ACID transactions. So why, at the end of the day, do you really want to migrate to Apache Iceberg? Some of the things I mentioned are clearly why, but I mean, you're going to have a more robust feature set because it's not just the improvements in performance and safety, but it's also there's new features you get when you migrate to Apache Iceberg, such as partition evolution, the ability to evolve your partition without having to rewrite your entire table. You're going to get compatibility mode, which basically allows, since Apache Iceberg isn't hung up on whether the files are in a particular directory, it can basically change the way it allocates the files for a particular table any way it wants, allowing it to do it in more efficient structures for different types of storage. This is particularly important when we're talking about like S3 object storage, where if you have too many files under the same directory or same prefix, you could end up throttling. So basically very large partitions could experience like bottlenecks. Apache Iceberg avoids this because it can then just distribute that same partition across multiple prefixes because they don't have to be in a particular folder to be recognized as part of that partition. It's based on the data, the metadata in those metadata files. There's hidden partitioning. So instead of having to like be the end user having to be aware of all these partition columns, what you do is you just express your partitioning as like a function on an existing column. So you can say, hey, you can do what's called a transform. So like a month transform on your timestamp. So then those who are querying the timestamp, even though they might not be aware of whether you're partitioning it by month or year, just by filtering on that timestamp column, they're going to get the benefit of whatever partitioning you've set up. Okay, so in that case, the end user has to be less aware of all these engineering decisions. They can just naturally query the table and get the benefit of that partitioning. Then there's like tooling. Okay, so in the world of Iceberg, Iceberg has become very ubiquitous among data tools. Most data tools either like support ingestion into Iceberg tables, they support reading Iceberg tables. Tools like Dremio can support like writing to Iceberg tables. So you have very extensive support across the board between different tools on how you can interact with Apache Iceberg. Okay, the benefit of this is you don't have vendor lock-in. Okay, you can have all your data sort of in this one format, and then as your tooling needs evolve, you don't have to re-migrate all your data. You don't have to recreate all your data because your data is in this one sort of universal format that has become fairly adopted across the industry. We also get the benefit of dataascode. Okay, basically you have this other open source project, Project Nessie, that has created a catalog for Iceberg that allows you to do things like branching, merging, so that way you can isolate ETL, and it does this at the catalog level. So if you make a mistake on 100 tables because of just this one automated ingestion job made a mistake across 100 tables, you can roll back all 100 tables by just rolling back the whole catalog one commit, or whatever to the proper commit. Okay, so this makes life a lot easier when it comes to things like disaster recovery, isolation TL work, multi-table transactions, a lot of really great use cases that makes life a lot easier and gives you some peace of mind when you're working with your data. So you have that, okay? And then you're gonna have openness, okay? Bottom line is like the actual development of Apache Iceberg is very transparent. I mean, there's public meetings, public lists, public Slack channel. Pretty much all the development discussions kind of happen right there in the open and allow anyone to participate. And you have a variety of companies who are contributing to the project, such as Netflix, Apple, Dremio, and more. Okay, so this is getting a wide variety of support and in a very open process. Okay, and then again, whenever you need help, you can head over to the Iceberg Slack channel where there's always generally people willing to help, and then you can even get support for different particular tools. As now that you're starting to see population of like vendor channels, so that way you can ask questions for particular tooling when it comes to Iceberg right there from the Iceberg Slack. So that's all really cool. So there's a lot of good reasons to want to end up in that sort of Apache Iceberg data lakehouse world. Okay, it just kind of gives you this totally much easier, faster world when it comes to managing your data. But we got to think about where are we starting from. Okay, chances are, if you are working in a sort of a legacy on-prem setup, you might be storing your data on Hadoop. Hopefully your data isn't Parquet files, but it might be in CSV, JSON files, depending what your setup is. But your data is being stored in this large on-prem network. You're tracking your tables using that Hive structure, using the Hive metastore to track those Hive tables, as I mentioned before. Okay, and so again, that's in the Hive table format. And you might be using Hive to do those queries. So then that means you write SQL queries in Hive, which then get converted to either Tez, Spark, or MapReduce jobs. Because again, Hive just basically what it does, it takes that SQL and then converts it into a particular job for a particular framework. Or you might be using other tools like Impala or um, Apache Drill in order to query that data in that on-prem data lake. Okay, and then you might be connecting to those sources using JDBC, ODBC. Okay, and then here you're starting to see like a bottleneck because JDBC, ODBC is a row-based connection interface. So you're serializing everything into rows when you really want it in columns. So you're saying you're going from column to row to column, which all that conversion, all that serialization eats up time. Okay, and then again, this whole setup isn't necessarily as fast as many of the newer technologies, and on top of it, it's really expensive to maintain. So it's slower, it's harder, it's pricier. Okay, but then eventually, like again, all your consumers can then get it into their favorite tools. Okay, through that JDBC or DBC connection. Okay, so that's where we start. Ideally, we want to have a situation where it's faster, easier, cheaper. Okay, so here's sort of like the end goal. So like basically, we want to go from starting place to this. Essentially, you're probably going to want your data on some sort of object storage. Okay, now if you're moving to the cloud, that could be S3, Google Blob Storage, Azure Blob Storage. Okay, one of these the major cloud providers. Okay, or you might still want to keep some of that data on-prem, and you might use, object S3 compliant project things like Minio or something like that, where your data is now in object storage, but on-prem, giving you sort of like still the benefits of the object storage, even though you're still maintaining your own infrastructure. Okay, but that data is going to need to be managed. Okay, because you're going to have your iceberg tables. You can optimize them yourself, but wouldn't it be nice if they were optimized automatically for you? Wouldn't it be nice to have that data as code to be able to do branching and merging so that way you can isolate ETL work, do multi-table transactions, roll back mistakes, all that good stuff? So that's where the DremioArtic catalog comes into play. So even if your data is on-prem, you could still necessarily catalog your tables with the cloud DremioArtic service. Because again, the catalog just tracks the location of the metadata. So wherever the metadata is, as long as your engine has access to it, it can just go to that catalog and be like, okay, that's where the table is. Okay, so we have that. But again, if you're using DremioArtic as your catalog, you're going to want your data in Apache Iceberg tables to get all those benefits that we talked about before. And then if you query that, you can query that table using Dremio Sonar. Okay, and Dremio Sonar is going to be a very key piece of this migration story because this provides a unified interface. The cool thing about Dremio Sonar, as you'll see in the next page, is that it connects to all sources. So it's not just your cloud data, but it connects to your on-prem data. And that's going to be a key point in creating that inflection point to easily migrate from sort of on-prem to cloud. Okay, so Apache Iceberg, we want to use Dremio Sonar because also it's very fast and very easy to use. It provides a semantic layer, so that way you can take all the data you have anywhere, curate it, meaning organize it into a semantic layer where basically people can see the data organized in some sort of logical way. So imagine like you organize it by department. But if you're doing some sort of like data mesh type setup, so you have a space for your marketing department, a space for your product department, a space for your supply chain, all these different sort of categories of data. So it's a lot, and then basically all of that will be documented via the wiki that's built into Dremio's semantic layer, and then governed through. So basically, you could have a data set that's made up of on-prem and cloud data, but with one set of governing rules that govern who can access it and how they can access it, instead of having to create governance and rules across multiple different platforms. So it gives you sort of a central access layer on top of that fast query engine. Okay, so that's Dremio Sonar. And you could connect the JDBC ODBC to Dremio Sonar, but ideally you connect using Apache Aeroflight. And with Apache Aeroflight, you're no longer having to serialize and deserialize between column and row, so you're going to get a faster connection. So overall, you're going to have a much easier to maintain infrastructure, okay? Because the benefit of cloud is you're just not maintaining all this physical infrastructure, and the benefit of using cloud services like DremioArtic and Dremio Sonar, you're not maintaining physical infrastructure for that as well. Or even maintaining cloud infrastructure for that, because Dremio will manage all that for you. So this becomes really easy to execute on. Okay, it's going to be much faster because you're going to get the speed benefits from Dremio Sonar's optimizations, from Apache Iceberg's optimizations, and it's going to be affordable. Okay, it's going to be way, way, way more affordable because you're not paying as much just to maintain the infrastructure. But on top of it, when you're using DremioArtic and Dremio Sonar and Apache Iceberg, you're going to really reduce a lot of your cloud storage costs and cloud compute costs to a minimum. And then all your users can just continue pulling that data into their tools of choice, whether they're using Jupyter notebooks, then pulling that into data frame libraries like pandas and polars, or pulling that into a DuckDB relation, or using Dremio Sonar's integrations to directly pull that data into a BI dashboard via Power BI or Tableau or some other BI tool. You're going to have that faster, easier, more affordable world. But sort of like as an interim step, so like the first step in the process, okay, is we're going to swap out one thing. So you're still going to have your data on, let's say, Hadoop, and you're still going to be using your Hive tables, you're still going to be using the Hive table format. But the first step in this migration story is to first use Dremio Sonar, the Dremio query engine, okay? The Dremio query engine, oftentimes starting off with like the software version to be able to query your data on-prem. The point here is to get your end users used to using the interface, okay? Because the idea is that if everyone uses this unified interface, later on when you move your data to cloud, there is no change to the end user. The end user is already used to how their workflows don't change at all, okay? Because Dremio Sonar as the access layer abstracts away where the data is, okay? All the end user cares about is what data is available to me in Dremio, and where that data exists on-prem or in the cloud won't matter, okay? Which allows behind the scenes for you to take the time you need to execute that migration quickly, but the workflow benefits have already kind of happened, okay, on the consumption side. So you start off, you create, you get your Dremio software or Dremio cloud setup going, okay, connecting to your on-prem world. But already your users can kind of see the speed benefits of Dremio Sonar, so they're already seeing query execution benefits. They're already seeing data transport benefits because now they can use Apache Aeroflight to pull in their data into their favorite tools. So they're already seeing, and you're already seeing, cheaper costs, easier use, and you're already starting to see the benefits of that semantic layer to kind of govern that data. And then what you can do is you're going to begin moving some of that data to the cloud. Okay, and the cool thing about Dremio Sonar is you can connect data, from your on-prem and from the cloud world. So now you basically have data in both worlds connected to Dremio Sonar. And again, your end users really don't care what the data is. They're just saying, okay, I want this data, I want that data, I'm going to join this with this, and they pull down the data via Apache Aeroflight or via one of the integrations or directly on the UI, however they want to do it. Okay, so basically that makes that whole thing a lot easier. Okay, so the Dremio interface becomes the access point. So that way, again, you're not having to have this constant friction of having to retrain the end user on how to use their data as you make this move. You just have to focus on actually executing the move. Okay. And then, at this point, you can either, be partially on-prem, partially in the cloud, or go fully on cloud as time goes. It just depends on sort of what your needs are, because you may have some data for regulatory reasons you have to keep on-prem, but you have a lot of data that doesn't, and you would like to kind of reduce some of those storage costs, reduce some of that maintenance, whatnot. And this kind of gives you the flexibility to figure out what that sweet spot is without having to really disrupt the life of your end users all that much every time you adjust it. So that's the beauty of sort of like this path, okay, of kind of migrating from on-prem to cloud. But again, the Iceberg piece, there's a lot of important decisions in sort of converting data that wasn't not Iceberg in that Hive format and converting it to the Iceberg format. And one of the first ones is choosing your Iceberg catalog. And there are several different Iceberg catalogs to choose from. Okay, so let's just have this chat, because this is always one of it's one of the most important decisions, and it's a fairly simple decision in the sense that like what the catalog actually does is very simple, but it has the choice you make can have some profound implications. Okay, but what the catalog essentially is, it's just basically literally an address book for where the data exists. Like it doesn't actually hold the data, it holds no metrics about the data, or at least most of them don't. All they do is they say, okay, the current definition of the table can be found here. Okay, which would just be like an S3 address. If we're talking about data on S3, it could be a Hadoop address. And then the engine just takes that address and finds that data and then goes and reads the table from there, wherever that pointer points to. Okay, so the catalog's location is independent of where the data's location is. Okay, the catalog just carries the address for where the data is physically, or where the metadata is physically located, and the metadata contains the location of where the data is physically located. So, I mean, very not very often the case, but theoretically, the catalog, the metadata, and the data could be located in 3 completely different places. Generally not the case. Usually your metadata and your data will probably be in the same place, even if they're not in the same folders or whatnot. But theoretically, again, the way Apache Iceberg works does kind of provide that, possibly that level of flexibility. Okay, so when you think about what your catalog is, it's a separate distinction from where your data and metadata is. But how does the engine find your metadata and your data? It starts off with the catalog. The catalog is what tells it where to look. Okay, so there's Project Nessie. Project Nessie is an open source project. It's the only open source project that was built specifically to act in this capacity, built specifically to be a catalog for tables like Apache Iceberg tables. And because of that, it builds in all sorts of really cool functionality, like Git-like functionality, which is really nice because again, you get that like multi-table, multi-table transactions, the ability to isolate ETL, all at the catalog level. Okay, and as that project evolves, it's going to be able to collect, be able to do all sorts of optimizations at the catalog level, collecting catalog level statistics that allow you to optimize your jobs and have all sorts of flexibility that just wouldn't be possible without that sort of catalog level abstraction. Okay, so it takes a catalog and kind of goes a little bit further. Okay, and it's open source, so you can stand up your own Project Nessie server if you'd like, but if you don't want to, you can use the cloud managed service, which is DremioArtic, which not only provides you that cloud managed Nessie server, but also provides you automated data optimization services and other cool features. Now, cons is, and this is going to be the same for like all catalogs, is basically there's always like the actual engine or tools that you use to read your Iceberg tables, they need to be able to read that catalog. Okay, and every catalog, while they generally all work from the same sort of base classes, they do have sort of differences in their underlying implementation. So each engine has to kind of say, okay, we're going to support this catalog. So with Nessie has pretty robust support between Dremio Sonar, Spark, Dremio Flink, Presto are all tools you can use. Okay, but if you're using, there might be tools that you don't. Okay, so you always want to check like, hey, my catalog, does the tools that I use to read my data read the catalog that I have? There are flexible ways to do that, and the whole catalog story is becoming more flexible every day, and I'll talk more about that in a second. But in the early stages, it was a big issue because it was oftentimes hard, if not possible, to move your data between catalogs. So if you chose a catalog that didn't work with your tools, it was kind of hard to read your data. But nowadays, again, not as much of an issue, and I'll talk about why. Okay, then there's the Hive Metastore. Okay, The Hive metastore, you can use the benefit of a Hive metastore is if you already have a Hive metastore because you're using Hive locally, you can just keep using that metastore. So you don't have to put up anything new. So it's a great starting point for your Iceberg tables to sit there and just keep them as part of your Hive metastore. And then later on, as you build out your infrastructure, maybe move them to another catalog that offers you other benefits. Okay, you wouldn't use this if you don't already have a Hive metastore, because there are other options. Okay, so you might as well choose something like Project Nessie if you have to stand up your own service already. Okay, AWS Glue. Okay, so this is the metastore for that's built into AWS. And the great thing about this is that it interops with like all of AWS services like Athena and Redshift. So if you're heavily using the AWS ecosystem, having your Iceberg tables catalog there can be uh, a nice way to get the most out of your AWS infrastructure. Although again, not every tool outside of AWS supports the AWS Glue catalog and reading Iceberg tables from there. So again, you have to take a look at your tooling and see like, okay, which catalogs support what. Again, this story is becoming less of a concern. More tools are supporting more catalogs, and there are other catalogs to talk about. So there's like the HDFS catalog, which is basically just you literally using the file system as your catalog. Okay, there is JDBC. Okay, that means you can literally use any database as your catalog. So the HDFS catalog just means literally like there is no catalog. You're just basically writing the you're writing the table straight to the file system in the same way like a lot of other formats work, where it's just basically the folder is your table. This is probably the most used catalog or the most used implementation for when people write tables with most tools because it's the simplest one. But again, ideal world, especially if you're looking to do a lot of concurrent writing, you do want some sort of actual like metastore type catalog in the long run. JDBC allows you to use any relational database that supports JDBC connections as a catalog. The issue there is whether the tool supports using a JDBC catalog. There's the REST catalog, okay? And the REST catalog, what it is, it's an open spec API. So this is open spec into the Iceberg that basically allows you to connect to any catalog that implements that specification. Currently, there is no open source implementations of that spec. There is currently one service that implements that spec in the form of Tabular. Imagine in the future, there'll probably be some open source implementations. There'll probably be other services that will offer their own proprietary implementations. So keep an eye out for that. Like it's basically what it does. It creates this one uniform interface that any tool can connect to if they support it. So again, as with everything else, always the issue is, do the tools I use support that catalog implementation? Okay. Can use the register table. Oh, let me just talk about that for a second. Remember, I mentioned that it's getting a lot easier to move between catalogs. So nowadays, if you commit to one catalog, you're not stuck with it. Like you don't have to move. Before, you would have to move your tables and you lose your table history. But actually, developed by developers here at Dremio, there's a method in the catalog abstraction called register table. It allows you to take the metadata from any other table in another catalog and register it with a different catalog. And very soon they're going to be coming out with a CLI tool to make that even easier to do. So if you just want to move table from catalog A to catalog B, you'll have a CLI tool that'll make this process very, very easy. Okay, so bottom line is like the catalog that you choose isn't as much a impactful long-term decision as it has been, because it's going to be much easier to move from catalog to catalog going forward with the register table method and soon the CLI tool. But generally, that's going to be the first choice. And again, based on the tools that you use and the support for the catalogs that those tools have, you make a choice for which ones best supports your needs. But once you kind of decided, okay, hey, this is a catalog I'm going to use, okay, then the next step is to figure out how you're going to migrate your data to different tables. So there's an in-place migration. This means you don't rewrite your data. So that's the beauty of Iceberg. Because the data doesn't have to be rewritten in a particular folder, because it's not dependent on a folder structure, even like some of the other newer table formats that still rely on sort of everything being in a single folder and co-locating metadata with the data. Since that is not a dependency, it's not a need, you can write metadata across files anywhere, which means you don't have to rewrite files or move files when you want to migrate, making the migration process a lot simpler. You can just say, hey, these are my files, make an Iceberg table out of them, and ta-da, you have an Iceberg table without having to write any new files. Just some metadata gets written. So that's an in-place migration. Then there's a shadow migration. Okay, and what a shadow migration will do is you're just basically creating a new table. So you are rewriting the data into an Iceberg table. This can be very beneficial because it'll give you the opportunity to, maybe change how the table's partitioned, change the scheme of the table, sort the table, take care of certain optimizations you maybe been putting off because you didn't really want to rewrite all that data earlier. But since you're migrating, you might as well take care of those optimizations now. So you'll have these different options. So how to do an in-place migration, how to migrate without rewriting your data. Now for Hive tables specifically, there is a procedure built into Iceberg called migrate. And what it does, it allows you to name the Hive table in your catalog, because again, these call procedures are part of the Spark libraries in Iceberg. So this is assuming you're doing this in Spark, although other tools and other engines will arise for doing a lot of these same things. But basically what you do is you type in migrate, okay? And what that does, it takes that Hive table from your Spark catalog and then converts it into an Iceberg table, okay? The problem is it's a one-way change. So once you've done it, you've killed the Hive table. So generally, before you do this, what you want to do, okay, is do a snapshot. Use a snapshot procedure, okay, which what it does, it creates a temporary version that you can audit and say, okay, hey, let me just make sure that the end result is what I expected. And then if you like the end result, you can then actually go through with the migrate procedure. So that's for Hive table, that's great. Now, what if you just have a bunch of Parquet files on your Hadoop that aren't organized into a Hive table, or you have Parquet files from a Delta Lake or Hoodie table or some other situation? You just have other Parquet files that are just sitting around, not in a Hive table that you want to add to an Iceberg table. In that case, you have the add files procedure. What the add files procedure does allows you to take any file or any directory of files and say, take these files and add them to this table. And it won't rewrite those files. It'll just write metadata that refers to those files. So those files are now a queryable Iceberg table with all the metadata that allows you to have those efficient query patterns, but without rewriting them. So that's the add files procedure, which is pretty cool. And essentially, those are sort of the two paths of doing an in-place migration. So you just want to just move data into an Iceberg table without rewriting the data. Another option you have is you rewrite the data, and you can do that using a CTAS statement. And this you can use any engine for, okay? Not just Spark. You could use Dremio Sonar to do CTAS statements. Each with their different, each of them have those little different nuances that give you different pros and cons as far as how they handle certain things. But it's as simple as this. You say, hey, I'm going to create a new table. Okay, so notice how this says prod.db. So prod would be my catalog, because this is generally how namespaces work in Iceberg. You always start off with the catalog and then it's dot, any additional namespace tokens. But I'm saying, hey, we're going to create this table using Iceberg. So this is Spark syntax. In Spark, you have to use this using Iceberg clause, so that way it knows you're using the Iceberg format. Partitioned but in this format. In Dremio, you wouldn't have to do the using Iceberg because that's assumed whenever you create a table or do any kind of DML. And then you can say how you want to partition the table, and then you put your select statement that selects the data from the original table. Okay, and the cool thing is that now it'll partition, when it rewrites that data, it'll partition it based on that new partitioning scheme. And who knows, you might want to sort it as well, so that way you not only get the benefit of partitioning, but you get a well-sorted partition. So that way you're writing the least amount of files possible. There's also, in Dremio, there's a clause called hash partition that'll pre-sort the data so that way you get the least amount of files possible in the partition scheme that you want. So you'll get a really nice, efficient, snappy table written on the other side, which can be to your benefit. So that's a nice thing about CTAS. You are rewriting the data, but again, because you're writing the data, you can take advantage to switch up the partitioning, to sort the data, update the schema, all these kind of changes that you may have been putting off. Now, best practices. So basic bottom line is when you start planning that you're going to do this migration, how should you start thinking about it? Okay, first off is to think about when I should use which procedure. So again, migrate is if you don't plan on using any data files. Okay, so you're not going to rewrite any data files, and you can't really update the schema or partitioning because you're using the data files as where they exist. So you can't really change anything because you're not rewriting the data. But that's fine. If all you want to do is just move the existing Hive table and move it to an Iceberg table, that works. Add files. Okay, that's again, those files are not in a Hive table, so you can't use migrate, then you can use add files. CTAS, if you want to rewrite the data, because you do want to update like the partitioning scheme and the schema and so forth, you can do that with the CTAS statement. And then register table, again, that's going to be for when you're really moving between different Iceberg catalogs. So if you do a catalog migration at some point later on, because you start off with Hive, and now you want to move over to something like Project Nessie, you'll be able to use that register table CLI tool when that's released. Okay, but bottom line, the actual like steps you want to plan, you want to kind of break down that process of migrating into like 4 phases. So first off, in the beginning, you're going to have all your consumers' tools should be reading from those old Hive tables, and all your writes should be writing to those old Hive tables. Then when you proceed to phase 2, okay, you've created this new Iceberg table or these new Iceberg tables, and now what's going to happen is that every read should still be going to the Hive tables, but all the writes should be simultaneously updating the Hive tables and the Iceberg tables. And then once you're confident that basically both tables are in sync and you're meeting your SLAs and it's happening, to your liking, that this Iceberg table is being updated, then what you can do is you can flip the switch, and now all the reads keep going to your new Iceberg table, and then all your writes still go to both because you may still, you want that backup while you make sure that everything's working fine. Okay, and then once you feel confident that everything's working fine and you don't need the Hive table anymore, you don't need to keep it in sync anymore, you can shut off the writes to the old Hive table, and now you fully migrated. All your reads are going to the new table, all your writes are going to the new table. So you kind of want to think of it in these milestones that might take, periods of time to accomplish, but this way, you're not moving too fast and ending up in a situation where you can't hit reverse if needed. Okay, so again, that just basically outlines what I just said. So with that ends today's presentation. So now we're going to be beginning the Q&A session. So if you have any questions, post them in the Q&A bar below, and we'll get to them. And thank you very much for coming to today's presentation.
Hey everybody. Okay, so we're going to begin the Q&A session. Hopefully you guys all enjoyed that presentation. And again, we do this every Tuesday, so always join us every Tuesday. Next week, we'll be doing even more on Hadoop migration, so definitely join us again next week. But let's begin going through the questions. Okay, so first question, and then actually, let me just answer that last question real quick. Can you please share the deck with us? Basically, once we post this online, so generally within 24 to 48 hours, this will be posted online. So it'll be posted on Dremio's website, on YouTube, and pretty much any podcasting platform you can listen to podcasts on. On the posting on the Dremio website, you'll also find a link to the slides and all the answers transcribed for the Q&A. So and that goes for all the previous episodes as well, if you're looking for those. And I think it's like dremio.com/gnarly-data-waves is the page. Okay. Cool. Now, first question. Once you copy metadata into Nessie, how do you keep it synchronized with the changes made in the source catalog? So bottom line is you always just want a catalog. So I think this is reference into sort of when you migrate, like use something like register table to register a table with like Project Nessie or vice versa. Generally, when you use that register table method, you move the table to the new catalog, and that new catalog should become your main catalog going forward. So in the sense that you don't have to worry about keeping changes in sync, because any future changes to the table are going to be done through accessing the table through that new catalog. And just to kind of recap sort of like that mechanism, essentially what happens is that, like, let's say I use like a tool like Spark or Dremio to write to an Iceberg table. It's first going to write all the data files. So basically whatever the result of the query is or the write job, it's going to write all the data files, then write all the metadata around those data files. Particularly at the end, that metadata.json file, that new sort of like table definition. And then what it does, it updates a catalog to point to that new version of the metadata.json. So basically what happens is if I originally had the table in Hive, all the Hive catalog is tracking is the location of that metadata.json. And then every time I write to the table, it's just updating that reference. Now, if I then register it with Nessie, all I'm doing is just taking, hey, right now the current metadata.json is this. I'm just going to move that reference over here to Nessie. And then on the next write job, as long as I send that write job over to the Nessie catalog, at the end of that write job, the Nessie gets updated. Okay. Now, if I had two catalogs at the same time, then I run into a problem, because if I do a write job to one catalog, it won't update the other catalog. Okay, so generally you want to migrate to another catalog, but you don't want to have two catalogs at the same time. Now, if you, for some reason, needed to do this, basically approaches you could have is by having some sort of like syncing mechanism. Basically you'd have to kind of write some sort of mechanism that notices that when one catalog gets updated and then runs like a register table job to update the location on the second catalog. That could be tricky. Also can run into potential consistency issues. So I generally wouldn't recommend that. Another approach you could take is that you can create your own custom implementation of something like the REST catalog. And then that could maintain multiple catalogs under the hood if you needed to. But again, all those kind of require a little bit more legwork. It's much simpler to just operate with one catalog and then use that catalog as the way I bring my tables from engine to engine. Okay, and that's the reason why you generally want a catalog and not necessarily the HDFS implementation. Because while the HDFS catalog allows you to write tables, there is no actual catalog that recognizes that all these tables exist. So there's no portable way for me to bring those tables from engine to engine, because there's no there's no catalog. There's nothing listing saying, hey, here are the tables that exist and where their metadata is. So generally you do want to use something like a Hive or a Nessie or a REST catalog or a AWS Glue, some sort of catalog mechanism. Because it just makes, not only does it allow like concurrencies like I talked about earlier, but it's going to, again, just make your tables more portable, because I can then just bring that catalog to whatever engine that recognizes it, and then all my tables are now available to me. Cool, so that's the first question. Let me just mark that. Next question. How do you coexist Hive tables and Iceberg tables for a while, since you have applications running on both time until applications are emigrated? Okay, so from a catalog point of view, if you're using Hive as your catalog, then both tables can exist in that Hive metastore. Okay, basically the metastore entries for the Hive tables are going to just be traditional Hive entries that just kind of track that these are the directories of the table and its partitions. And then the Iceberg metadata entries are just going to be like, hey, here's where the metadata.json is. And then from the engine's point of view, it's just going to, Spark knows how to read a Hive table and an Iceberg table. So it's just going to hit that catalog and apply that right read path based on, hey, I know this is this kind of table. I'm going to read that Hive metadata this way. I'm going to read that Iceberg metadata this way. So generally, if you're doing that migration, Hive is a pretty good catalog to start out with, because you can coexist both types of tables in it. Now, as far as like keeping them in sync, again, that's just going to be based on having to the way you write your write jobs. So basically, you could write them in a way that basically writes the same data to table A and then to table B. But essentially, as far as the catalog goes, they can coexist in the same Hive catalog, Hive metastore. And then again, later on, you can always transfer that over to a different catalog using that register table method once you've completed that migration. Okay. But bottom line, with tools like Spark and Dremio, they know how to read Hive tables. They know how to read Iceberg tables. So there shouldn't be an issue with the tools being able to see and read both types of tables from your Hive metastore. Okay, so you said new catalog becomes your new catalog. Does not work with coexistence situation I mentioned above. Okay. Maybe I'm not fully appreciating what you mean by coexistence. Like, are we talking about coexistence of two catalogs, or we're talking about coexistence of two tables? Because if we're talking about two tables in the same catalog, then a Hive table and an Iceberg table can coexist in the same catalog. But can the same table coexist in two catalogs? That's where you run into issues, where I basically have the same table being referenced into two catalogs, and I'm making updates from both catalogs, because then those updates won't be in sync, because one catalog won't be updated when I make changes from a different catalog. Okay, got it. So it looks like, okay, so I think press that. So let me just mark those. Okay, with Iceberg, how does metadata update work with writes happening from different processes engines? Okay, so basically the way the write's going to work and how we handle the concurrency. Okay, so essentially what's going to happen is that whenever you write, essentially the first thing it's going to do, it's going to read the catalog. The catalog is going to point to the newest metadata.json, and the metadata.json, which is like basically defines the table, is going to have some sort of like ID, some sort of sequence number. And what it's going to do is that before it does anything else, it's going to project saying, hey, keep it simple. We'll say we're looking at snapshot number 3. So I'm about to write snapshot number 4. So it knows before it does anything that when everything is said and done, I should be writing snapshot 4. So then it's going to go and do its job and start writing all of the data files that it needs, then writing the metadata on those data files that it needs. And before it actually makes the update to the catalog, or actually even before it writes the metadata.json, it's going to double check saying, okay, let me take a look at the catalog one more time, see what the newest metadata.json is, make sure it's the same one. And basically, if I go back and I look, hey, now there's a snapshot 4. So like somebody else wrote snapshot 4 while I was writing mine. Well, then I know I need to rewrite my snapshot. So I need to go, okay, now I got to rewrite. I got to write snapshot 5, and I got to reconcile these 2 snapshots. And it'll basically take a look at the changes. And if none of the changes are conflicting, it can just say, write a new metadata.json and say, okay, this is snapshot 5. And you don't have to rewrite all the files. But essentially, this is what's referred to as like optimistic concurrency. So basically, I'm going to write the job assuming it's all going to go fine. But at the last second, I'm going to make sure that my projected snapshot is still accurate. And if not, then I reattempt. And then basically, usually there's like a certain number. I think by default, it's like 3. So it'll reattempt it 3 times. So basically, that snapshot keeps updating before I finish my job. And after 3 times, then like the job would fail. But the idea is you're never going to have you're not going to have 2 jobs collide. You're not going to end up having inconsistent data because you have concurrent writers. So either, one job will just have to reattempt after the first job succeeds, and then you end up with both jobs being completed at the end, but consistently. But you're never going to have like, hey, one job writing over data that was just updated from a previous job. Like they're reconciling with each other, thus giving you those asset guarantees. Now, of course, if you had like 1,000, like, you're probably not going to have like, you probably have like, a handful of writers. So then that concurrency shouldn't be too much of an issue. You have lots and lots and lots of writers, and that becomes a little bit trickier. But again, then you have to start thinking sort of, how are you doing these large writes, or are you doing small writes? But the more writers there are, again, the more likely, okay, hey, I don't meet my projection. I got to redo the job until I do hit a number, till my projection matches up with my projected number. But again, you'll never, have 2 writes at the same time that conflict with each other. It'll always just be try it again. So that's essentially how that will be prevented. Okay, and again, it doesn't even matter what engine it is. So basically, if I had 2 writes coming from one from Dremio, one from Spark, they're both doing that. So essentially, like, Dremio's is done writing and realizes, hey, the Spark job finished first, it's going to reattempt it and make the next snapshot. So it doesn't matter what engine it is, they're all following that same process. Okay, how is compaction triggered in scenarios like streaming ingest, where we are accumulating lots of small Parquet files? There's a couple different approaches to this. If you asked me like 2 months ago, I would say, well, you just have to manually, do compaction or write a service that automates but luckily now we have a embarrassment of riches where we have now many options to automate that. So Dremio, with its DremioArtic catalog, which is powered by Nessie, now has automatic table optimization. So you could just set optimization on a schedule. So that way it's just compacting the files, like let's say every hour or a half hour or 5 minutes. And then that way, basically, if you're ingesting streaming data into a table, it'll just get compacted. Tabular also has a similar service. OneHouse, which does streaming ingestion, while they do streaming ingestion into Hoodie, the cool thing, they have this thing called OneTable, which will allow you to sync that metadata as Iceberg metadata into an AWS Glue table. So you'd still be able to read it in Dremio, and then they would also handle the compaction on their end. So basically, you have a lot of different options on how to handle that data. And then again, with Tabular, they also have like an AWS Glue sync mechanism. So for reading that data in Dremio, you would use the AWS Glue catalog for OneHouse and Tabular. And for DremioArtic, you would just use the DremioArtic catalog. And again, there's a automated table scheduling. You just schedule it when you want it to happen. So now you have a lot of options for how they have that just automated for you, but you can always also create custom services. So it could just be as simple as like writing a Python script that just sends because now Dremio has this optimize command that does the compaction, or you could use Spark that has the rewrite data files procedure. And you could just write like a Python script that just sends the appropriate SQL to the appropriate engine, and then set that as a cron job. So there's always those, if you need to do something that's a little bit more granularly controlled, But again, you do have options on how to automate that now. Cool. And let's see what other questions we got. Another question, if I migrate to Iceberg, how would I keep my tables optimized? Must I do this manually? I just literally answered that. So again, you could do it manually. So you could just run those compaction queries manually. You could set up cron jobs or set up even like REST point triggers. So you could do something like basically when data lands in your S3 bucket, it triggers a Lambda that then sends the SQL query to Spark or Dremio, runs the optimize command on Dremio or the rewrite data files procedure in Spark. There's a lot of different options on how you can set up that automation if you're doing it manually. And then of course you have all these services that provide you automated table optimization now. So basically the Iceberg story with the ability to move between catalogs, the ability to automate your tables, optimize your tables, and also just a lot of the defaults especially with the latest update, a lot of the defaults are even better. So which is going to improve performance out of the box. Because before the performance was always there, but some settings you had to change. Now like the defaults are set where you're going to get even better performance right out of the box. So right now today is always a good time to try out Iceberg. And then last question that I see right now, how can I get started with Dremio? How much would it cost? Now, when it comes to getting started with Dremio, basically you can get started for free. There's two routes. So basically, if you mainly are, as far as your cloud infrastructure goes, if you're mainly using like AWS, you can sign up for a Dremio cloud account in like 5 minutes, probably less, and get started and get going. And you can start for free. And then when you feel like you want to bump up to like enterprise level packages, you can do so. But basically you can just use it for free. The only cost would be any infrastructure cost of like AWS instances you use for running your clusters. But nothing but from the Dremio perspective, you're not paying us any licensing or whatnot until you upgrade to a paid package. If you're on-prem, if you're using Azure, we do currently have like Azure version of cloud in private preview, so you can talk to us and we can figure that out. Or what you can do is you can use Dremio if you're using Azure, Google Cloud, or on-prem, or any miscellaneous type of infrastructure. You can use the Dremio Community Edition. That's the free open source copy of Dremio, and you can deploy that to your own cluster. That cluster can look any way you want. It can be anywhere you want. It's basically you set it up, and it can access all your sources, and you can execute all this as we said before. And then when you need some of the more advanced security features or some of the more advanced features, you can then upgrade to Enterprise Edition and have a chat with us, and we can talk to you about how that works. But at the end of the day, the starting point is free, either through Community Edition if you're talking about on-prem, or talking about cloud. In the cloud world, either way, like there's a free way to just kind of get started, enjoy the benefits of Dremio, and kind of move forward from there. Okay, is it possible to write from Kafka to on-prem Nessie and Iceberg? Did not see that in the Nessie compatibility slide. Okay, at the end of the day, like far as the compatibility with Nessie, the compatibility with the catalog, you can stream into anything. Essentially, what matters is what engines support the catalog. So in the case of Nessie, right now you do have Flink support. So really what you would probably do is go from Kafka to Flink to Nessie. So basically you would stream into Kafka, and then Flink would pick up on that Kafka feed. So we'd use Kafka as a source and then sync into Iceberg and Nessie. But that would sort of be my current recommended approach. The other approach is you could, again, I mentioned OneHouse earlier, they have they do streaming in the hoodie, but again, they can translate it into Iceberg, which you can then access to the AWS Glue catalog. So that's another service you could use for streaming your data in. Except that you'd be using technically AWS Glue there. But, in the future, we'll see. Everything is going to kind of be everywhere in the future. It's always just a matter of when. Does Community Edition have Nessie and Arctic? Okay, so essentially Arctic is just a Nessie catalog. So anything that can connect to Nessie can connect to Arctic, the cloud hosted catalog. So the Arctic service is a cloud service because it's not just the catalog, but it's all the optimization services and all this other stuff. Now, I think in the next version of Community Edition and software, so I guess that would be version 25, they should be adding a Nessie connector. So that Nessie connector could be used to connect to your own deployed version of Nessie. So if you just want to host your own on-prem version of Nessie because you need to, because you can't use cloud infrastructure, or if you wanted to use the DremioArtic catalog, so while the catalog is hosted in the cloud, your on-prem Dremio could still connect to it via that Nessie connector, and you could still enjoy all the benefits of it. Because at the end of the day, the catalog is just basically a pointer to where your metadata exists. So it doesn't matter if your metadata exists on-prem or wherever it physically exists. The catalog is just a way for the engine to know where it exists. So that would be the story once on that next version, once that Nessie connector is added to the software version of Dremio. On the cloud version of Dremio, you have DremioArtic built in, literally like it's just integrated into sort of how you use the Dremio itself. Like you can just one click, you have a catalog. It's super easy to use and really neat. I definitely like playing with it quite a bit. But again, that Nessie connector should be coming very, very soon. And so, okay, well, it's been delightful. You guys asked a lot of really great questions, a lot of really interesting questions regarding, these migration patterns, regarding using Iceberg. Yeah, that was the question I was answering before. That was basically saying Community Edition in the next version should have a connector to Nessie. So in the next version, you'll have a Nessie connector, which you can then connect to your own deployed Nessie or to the DremioArtic cloud version. So DremioArtic is always going to be cloud, but you'll be able to connect to it from software using that Nessie connector. So that was the answer to that question. Okay, but again, next week we'll be talking about 5 reasons why you would want to migrate from Hadoop. So if you want to go dive even deeper into this whole Hadoop migration story or Hive Hadoop, so there's no way to use Nessie from the community edition in its current edition. Correct. So right now with version 24, there isn't a native connector for Nessie at the moment. So should be again version 25 where that'll be introduced. Last I checked. Okay, Nessie itself, no. Basically, Nessie is a separate piece of software. So there's a Dremio Community Edition, so that's like the query engine. Okay, and that can connect to all sorts of different sources. Like it can connect to AWS Glue, it can connect to Hive, it can connect to all sorts of different things. So Nessie would be a separate sort of meta store that you could deploy, or you can get the cloud software version, which is the Dremio Cloud Arctic, and then the Dremio query engine would then connect to that. So the Dremio Cloud can connect to Arctic currently. Dremio software, the community edition and enterprise edition, will soon have a Nessie connector added to it, which you can then connect to a Nessie or Arctic server. So again, the catalog is always a separate service than the query engine service. So yes, so bottom line, cloud, you have full access to the Arctic catalog. On software, so again, self-deployed, you will have access to Nessie Arctic very soon. But right now that connector is not built in. You could build in a custom connector, and I'm not sure there might be a community connector that exists, but it's not a native connector will exist in the upcoming version. Okay. Correct. So Nessie, you can stand in your own environment, or you can get the cloud-hosted DremioArtic, which is basically a SaaS version of Nessie. So again, basically, to repeat that question is just clarifying is that Nessie is a separate project. It's a separate open source project. It's a metastore that you can stand up, but DremioArtic is a software as a service version, or basically a catalog as a service version of that Project Nessie project. So with no further ado, I will see you all next week for more Hadoop questions. We also got a bunch of other presentations coming up about automated table. We have a whole thing about automated table optimization. It's going to go dive deep into like Dremio's automated table optimization features. We have all the stuff about dataascode, all sorts of really good stuff coming up. So make sure you keep tuning in every week, whether you come live or you subscribe on our YouTube channel or subscribe on your favorite podcasting network. But we got a lot of great stuff coming on Gnarly Datawaves on the way. Thank you very much once again for joining us. I'll see you all next week.